So we're going to talk about the London Eye, an interesting and challenging problem that starts with a Ferris wheel. We're told a little bit about it, and our Ferris wheel over here, we are told has a diameter of 135 meters, and we are also told that it takes 30 minutes for a full revolution of our Ferris wheel. We're also told that it connects up with the ground, so someone can get right on at the bottom and then take 30 minutes to go all the way around. And as they go all the way around, right, they're going to have different heights as time goes forward. And our goal is to model that height of a passenger as time goes forward using a sinusoid. Let's not worry what a sinusoid is right now. Let's just try to get a feel for the basic shape of this height function. All right, so if we come over here and look at our passenger, he gets in at ground level. Then as the Ferris wheel starts moving up in height kind of slowly, and then maybe a little bit faster, and then leveling off near the top, starting to come down, coming down a little bit quicker, leveling off near the bottom, and so on. With that picture, that little movie in our mind, pause the video and see if you can, over here, draw a sketch of the basic shape of our height function. All right. Well, here's what I'm getting. Our passenger starts at ground level, so height 0 at time 0, and as time goes on, his height starts moving up a little bit slowly, then more quickly, and then levels off, and then comes back down. So something like this. Coming down, leveling off, and then at the bottom again, right? And then if he stays on, they can continue on the Ferris wheel. And so here's the basic shape of our height function. And the idea is, right, because it's just going to oscillate back and forth like this, it kind of looks like a sine or cosine curve. And that's pretty much our big observation here, that this looks like a translated sine or cosine curve. And that's exactly what a sinusoid is. And so we just need to pick one of these, and just to make a choice, let's choose sine and see how we can translate it to match up with our curve here. And before we do that, we can add a little bit more detail here, right? For example, we know how high our passenger is going to get, right? At the highest point, right, the height is going to be 135. Right? That's the diameter of our Ferris wheel. So 135 at the very top. And since it takes 30 minutes to swing all the way around, right, the next time our passenger reaches ground floor here will be at 30 minutes. So with that info, let's see if we can take our sine function here and mess with it. Now, one of the first things that we can do to mess with and translate a function is to add something afterwards. And this has the effect of pushing our graph up and down, right? Just a vertical translation. We can also, if we subtract something from our variable inside, that's going to have the effect of a horizontal translation. So moving our graph left and right. If we multiply our function by a number out front, this is going to stretch our function vertically. And lastly, if we multiply our input by a number, that's going to stretch our function horizontally. And so these are the 4 basic transformations we can do, and we want to see how we can use these starting with just a good old-fashioned sine function to match up with our curve here. To help us do that, let's jump over to Desmos. All right, so in Desmos, it doesn't like sine of t, so I'll use x as the variable. But if you're inputting this into WebAssign, make sure that you use the variable t, because that's what it's expecting. If you give it an x, it'll be all confused. Anyways, here is our good old-fashioned sine curve wobbling back and forth between -1 and 1. Right? So let's first think about multiplying, oops, I guess I can just do it right here, a number at the front. So we can quickly add the slider there and see what happens for different values of this number. Notice if I slide this up, our graph is indeed getting stretched. Right? And so, for example, if I stretch this to an a equals 4 value, notice now that our graph is going from -4 at the bottom to +4 up top. This a is actually called the amplitude of the sine wave. And it just tells us, starting from the middle of the wave, how far out to get to the end. And so for us, that's 4. And our curve is doing a full stretch of 8, right, from the bottom to the top. We'll think about our curve for the Ferris wheel. From the very bottom of our curve to the top, how far do we want our curve to stretch? It's going to be that diameter, right? 135. We want our fastener to get on at the bottom and then rocket up to a height of 135. And so because the amplitude is half of this stretch, we're going to want the amplitude here to be half of that. So maybe, let me just give us some clean values here. And so half of 135 is 67.5. So I'll slide this up. And noticing from our graph, doesn't look so clean anymore, we can zoom out actually by holding Shift, and I'm going to drag on this y-axis and pull it down. Try to get a better picture here. There we go. So here is our curve. Next, let's think about adding a number at the end of our function. Again, this has the effect of shifting our graph vertically, just pushing it up and down. All right, but think about this. Right now, our graph has our passenger starting at height 0, shooting up, and then shooting back down, hitting the ground, and then burrowing underneath it for a while. Right? We want to push our graph so that it's actually not going underneath our t-axis, but it's just bouncing up and down on top of it. With that in mind, what should we shift our graph by? Well, because our graph, right, is going to be dropping down by that 67.5, that's what we need to push it up by to get it bouncing on our t-axis. Once again, I'll just choose some clean values here for d, and we'll push that up to 67.5. There we are. And now our graph is bouncing up and down on the t-axis as we'd like. All right. It's not doing everything we want. For example, right now it has our passenger's starting height at, like, I don't know, 65-ish. And also it's not taking 30 minutes to go through the revolution here. So those two things we'll have to adjust with our other transformations. Switching back over to our notes, our horizontal stretch B actually has a very clean connection to the period of our function. In other words, the length of time it takes for our function to repeat itself, say to get from the very bottom back to the very bottom again, right? And handily, we know the period for our function. And the formula, it turns out, is that this b is 2 pi over our period, which for us is 2 pi over 30. So we know that, and so we can pop that into Desmos. Add the b in there, and I'll just set that equal to 2 pi over 30. And now our graph is a little bit widely spaced. Let's hold shift, click on the t-axis, and drag that in. All right, now it's looking a little bit better, and indeed notice at the bottom over here on the left, that's happening at negative 7.5. The next time that happens is 22.5. Now if we add 7.5 to that, indeed we get the 30 minutes that we want to see from the start to the end of our passenger's ride. So our period is all set. The only thing that's left to do is to shift this left and right. And again, the way we do that is by subtracting a c from our variable x. And right here, this will now have the effect of moving our graph left and right. And we just need to now figure out which c value will shift our graph over and make the bottom start right where we want it at height 0 at time 0. I'm going to leave it to you to play around with this and figure out what c will work. You can just bring up Desmos and quickly recreate this if you'd like. You can do it. That's all for now.